Hello dear students, I am Professor Priya Kulkarni, and in this session we are going to learn about the flexibility matrix method for one end fixed and other one is hinge. In the previous lecture we have seen one numerical for simply supported, means both ends hinge condition, and in this lecture we will see one end fixed condition and another one is hinge. So this is the given problem statement. Support A is fixed, support C and D are roller supported, okay, and AC span is loaded with a 60 kilonewton load, loaded exactly at the center of the span, and 10 kilonewton per meter UDL is there on the CD span, okay, and CD span is having length of 6 meter, okay. So this is the problem statement and we have to solve this continuous beam by using flexibility method. Now first step is to determine the degree of static indeterminacy. Once we get the number of unknowns, or here we can say number of redundants, then we are it will be convenient, or it will be focused, so that we can solve for the unknowns or redundants, okay. So first of all, step 1 is finding the degree of static indeterminacy of the structure. To find the static indeterminacy, what we do number of total unknowns minus total minus equilibrium equations, okay. But for the beams we can neglect the axial force, okay. So we neglect axial force in terms of unknowns and we can neglect in equilibrium equation, okay. So it have to be biased, that we have to neglect in both the cases, for unknowns and for knowns, okay. Now this is the A support is fixed, it has two unknowns neglecting axial force, one is movement and another one is vertical force. We are going to neglect this axial force, okay. So it has two unknowns here, then it C support is roller, so roller support has one unknown, and uh, D support is also roller, so it has one unknown. So total unknowns are 4 if we neglect. Okay, okay, and then what are the known values, or what are the equilibrium equations? Equilibrium equations are summation of moment is equals to 0 and summation of vertical forces is equals to 0. It means we have two unknowns neglecting the axial force. So 4 minus 2, it will give you the 2. So 2 redundants are there, but here I have not neglected, okay. I have taken all the unknowns, so 3 unknowns for the fixed end, 1 unknown for roller and 1 unknown for this roller again. So total 5 unknowns minus 3 equilibrium conditions we know, so it will give you 2 unknowns, okay, 2 redundants, okay. I have shown you in the both ways. If you doesn't want any confusion, then just don't consider that neglecting part, okay. Then step number 2 is identifying the redundants and assigning coordinates. Now we have two redundant values, okay, as per the degree of static indeterminacy. Then we have to identify those redundants and we have to assign the coordinates, means R1, redundant 1 and redundant 2, okay. Now here what we'll do, or we can consider RC, this is also unknown value, and RD, this is also a unknown value, okay. So in this case we are going to consider, or we are going to assign the coordinates R1 for RC and R2 for RD, okay. I have made a mistake over here, I have to consider this as B, but I have written just RD this one and RC is this one. I have written RB over here, okay, it is RD, okay. Otherwise we only consider R1 and R2, so these two are the redundants for this case. Okay, now what is the next step? Next step is to remove the redundant force and get a release structure. Okay, that is M diagram. And second step is M1 diagram, that is we are going to we are not going to consider any loading, but we will show the release structure with a redundant one, and the next diagram we show the redundant with two without any loading. Okay, now just look at here. So this first one is the loading diagram as given in the numerical. Then this diagram, M diagram. Okay, in the M diagram or release structure actual movement diagram, we are not showing any redundance. Okay, we have not shown any support over here, and also we have not shown any support over D point. Okay, so it is kept blank, but it is shown with the loads, given loads. Okay, in the third diagram, that is M1 diagram, release structure with redundant R1 is equals to 1, that is M1 diagram. R1 is 1 means what? We are going to apply unit load over there. Okay, so for M1 diagram we have not shown any load, we just have shown the shown the beam and only one redundant over here. This is for R1, that's why it is M1 diagram. Okay, then moving towards the fourth diagram, I have shown the second redundant, that is R2 is equals to 1, that is RC is equals to 1 over the M2 diagram. This is for redundant 2 diagram. Okay, so these are the important diagrams. Okay, I will repeat once again. In the first diagram you have to show, you have to remove the redundants, you doesn't need to show the redundant values and supports, whatever the redundants you have considered, just show only loading diagram without redundant. Okay, that is release structure. Here we have released the redundants. Okay, in the next diagram, if there are two redundants, then you have to show two diagrams, M1 diagram and M2 diagram. M1 diagram is for redundant 1, and in the redundant one you have to apply a unit force 1. Okay, and second next one diagram is for redundant 2, that is M2 diagram, and there you have to show the unit force for that redundant. Okay, so I think it is clear to you. Now one question arises over here, that why we haven't considered any movement as a redundant. Okay, I'll tell you, for the simplification of numerical and for time being, we have considered only reactions as redundant. You can consider movement as redundant. Okay, but it will take some time, or it will take more time than the reactions. Okay, you can consider movement also as a redundant. Redundant means the unknown values. Okay, moving towards the next step. Okay, just a minute. This is the next step. Now what we have to do here, we have to consider the or we have to draw one table for movement M1, M2, limits, origin and zone. Okay, so first table, we'll make one table, and first row is for zone, that is span, DC, CB and AD. Then origin, I have considered origin D over here for all the spans. You can consider separate origin, but you have to take limit according to that. There is no problem, whatever origin you are considering, you can consider of your own interest, but you have to just be careful with the limits. Okay, then M, movement diagram, M1 diagram, M2 and limit. Okay, so whatever the diagrams we have seen, according to that we are going to form these equations. Okay, now we will consider the zone DC. just a second, it has some. Now what we are going to do, we are going to consider this zone DC. Okay, D is the origin and limit is 0 to 6. Okay, then here what we are doing, we are going to consider one section. Okay, we are going to cut the CD span and we are going to consider this distance as x. Okay, and we take the moment with respect to this distance x. Okay, now just CD span is loaded with a UDL of 10 kilonewton per meter. So and this is downward load, so it will create a anti-clockwise movement like this. Sorry, it will create a clockwise movement like this, and clockwise we are considering as negative. Okay, clockwise we are going to consider as negative. So this is the case for CD span. So we will take the moment, that is 10 into x square by 2. So this is the moment for CD span. Now what is the next span? It is CB span. Okay, CB span. Here we are going to cut the section over here like this, and we are going to assume, or we are going to consider origin as here C or D. You can consider of your own choice. If you consider D as origin, then it should be limit between 0 to 6 plus x. Okay, sorry, you have to consider 0 to 6 plus 3 is 9. 0 to 9 will be the limit for, if you consider D as origin. Okay, and for this BA span, sorry, for this BA span, if you consider D as origin, then limit will be 0 to 12. Okay, this will be the limit. But if you consider for the CB span, if you consider C as origin, then it will be 0 to 3. Similarly, for BA span, it will be 0 to 3. Okay, like this. Now we are going to cut the sections, and where we got any point load or any change in the coordinates or variable, then we are going to consider those spans separately. Okay, so we have 3 spans or 3 sections that separately we have to consider. First one is CD, and second one is C to B, and that point we have one point load, and then B to A. Okay, and accordingly we are going to cut those sections, and we are taking the movements. While taking the movement, you have to consider whole loads from this point. Okay, you have to consider all the loads, all the movements, all the reactions, whatever coming in your way, you have to consider from the origin or the starting point. And also, why we are going to consider the separate or a single, means what RC and RD as the unknowns? Why not the vertical reaction at A as a unknown or redundant? Just because for the simplicity. Okay, our structure looks like this. Okay, we have not considered any redundant, so it looks like a cantilever beam. And in any case, cantilever beam solution or solving the simplification of cantilever beam is much more time consuming, and it much more easier. That's why we have considered such a redundance. Okay, so we'll form that table by considering the movements. What we have done with M1 and M2, for M1 and M2 diagram, we have drawn that M1 and M2 diagram. This is M1 diagram and this is M2 diagram. Again we have to cut the sections accordingly, and we are going to consider all the distances with respect to x, and we are going to consider those moments for M1 and M2. Okay, it is clear to you? Okay, this is very much important table, and from this table we are going to solve the next part. But this is very important. You take time to uh, draw these equations or take these movements, but just be careful with this table. Okay, now next part is the directly calculation part, solution part. That is, we are going to form the flexibility matrix. So, displacement of a release structure in the direction of redundant due to given loading. We are going to form displacement. We are going to form displacement due to redundant 1, also displacement due to redundant 2. So, these two values we are going to form or solve for these two values. Now, what is the displacement of release structure due to redundant? That is, it is the m into m1. Okay, for redundant 1. Okay, now what is the m value? This multiply with this. Okay, then this multiply with this, then total this multiply with this. Okay, so we are going to form the dr1 coefficient. Okay, displacement of a relay structure due to redundant 1, and we get one value in terms of EI. Then for displacement or release, displacement of release structure in the direction of redundant, for second redundant we are going to multiply m into m2, m into m2, okay, this into this. Okay, and limits part will be the common for all m1, m2 and m diagrams. Okay, so we are going to solve for this and we get this value in terms of EI. Okay, is it clear to you? So this is for displacement coefficient. Now for flexibility coefficient, we have to apply a unit value over that particular redundant. Okay, so just carefully listen these two lines. The displacement at the first place due to redundant 1 and displacement at the second place due to redundant 2, sorry, due to redundant 1. It means for the two places, that is two places means was R1 and R2, and we have two redundants. So we have 4 coefficients, or we can get the 4 coefficients from this. That is due to redundant 1 at the positions first and second. Okay, so here we get 2 coefficients, and due to redundant 2 at the positions 1 and 2. So here we get the 2 values. So total 4 by 4 matrix we are going to form. Okay, is clear? So F11 is what? It is due to redundant 1 at the first place. So M1 into M1, that is M1 square, limit in integration limit 0 to L m1 square into dx upon ei. So this is the F11 matrix, and we are going to take a form a square this m1 matrix. Okay, so directly we have done square square square, m1 into m1, m1 into m1, like that. Okay, and we have solved for this. So we get one value, we got one value in terms of EI. Similarly, now here just look at here, displacement at the second position due to redundant 1, that is F12. Okay, and displacement due to redundant 2 at the first place, it's F21. And what is the how can we get those flexibility coefficient? That is by multiplication of m1 and M2. Okay, it is clear. It may take some time, but just be clear with the concept. Okay, since we have chances of getting online exam, so just be clear with the concepts. Okay, so we by doing this we get F12 and F21 coefficients. Now last coefficient is F22, that is flexibility coefficient, that is due to redundant 2 at the position 2. Okay, so it will give us F22, and what, how to get that F22 matrix? M2 into M2, that is M2 square. So we are going to directly make a square of these two values, and then we will get the matrix value F22. Now this after doing this we will come to the final step, that is forming the flexibility matrix or forming the compatibility conditions. By using compatibility conditions we are going to form the or we are going to found the redundant values. Now here in this numerical we doesn't have given any sinking, or we doesn't have given any displacement value, okay, or any rotation value. Okay, so displacement at 1 in the release in the indeterminate structure is equals to 0, and displacement at second position due to this in indeterminate structure is also 0. If we have given any sinking of the support, then we can put that value in particular place, but we doesn't provided any sinking or any displacement in the numerical, that's why we are going to keep it as equals to 0. Okay, now by using compatibility conditions, this equation we are going to form, that is displacement in the indeterminate structure di is equals to displacement due to in the release structure flexibility coefficients into redundants. Okay, so di value we have 0, we have taken ei as common, dr flexibility matrix, and r is r1 and r2, it has cut over here. Okay, and we get equation in terms of two unknowns, and we are going to solve that equation in the calculator and we get those values. Okay, if we get the positive values, then whatever assumption that we have taken that redundants are in upward direction, that is true. If we get any value negative over here, then we have to change the our assumption that some of the value is going downward. Okay, so this completes our numerical, and the last step is to draw the shear force and bending moment diagram. Okay, so this will complete our one numerical. I have done will consider sinking of the support numerical in the same case, for the same case. Okay, so this will complete our one numerical for both ends hinge condition, and the next type of numerical is by considering sinking of support. So here what I have done, I have taken the same numerical and same numerical diagram, and what is given in the problem statement, it is support sink by 25 mm. Now which support C, this is C and D. So this central support sinks by 25 mm and EI value is 3800 kilonewton per meter square. So this thing is given. So where we are going to use this sinking of the support? We are going to use this sinking of the support for the DI values. Okay, we have considered RD as redundant 1 and RC as redundant 2. So we doesn't have any displacement at D point, so we have considered DI1 as 0 and we have sinking of the support at the second redundant place. That's why it is 25 mm, and sink means what, it will go downward. Okay, so that's why we have considered minus 0.025 meter. So this value will put for di2 here. Okay, is it clear? Keeping all the steps up to step number 4 same, only we have change in the total displacement di value. Okay, that's the only change if we have given any sinking of the support. All the steps up to step number 4, that means for finding that steps up to finding or calculation of flexibility coefficient, all steps are same. Okay, now now how to calculate the equation I have shown over here, that is this 576 175. So and here it is r1, it has cut over here again, r1 and r2 is here. Okay, 1 upon ei r1 and below 1 is r2. So 576 r1 plus 175.5 r2 is equals to 25110. Okay, then 175.5 r1 plus 72 r2 is equals to 8910 minus 0.025 into 3800. 3800 is the ei value, and we have to shift this ei over here. Okay, so it will get into multiplication with this 0.025 like this. Okay, so we get two equations, first and second equation, and by using calculator, using equation mode, equation 2 and unknowns 2. Okay, two equations, two unknowns, so we can easily get the unknowns in the calculator. Okay, and here also we get both the values positive, that's why we have considered upward sign is okay, is right. Okay, so this will complete the sinking of the support numerical. Last step is to draw the shear force and bending moment diagram. Okay, it doesn't have any change because of sinking. Okay, so this is the problem statement and numeric solution for the both end one end fixed and another end hinge, and by considering sinking of the supports. Okay, so you need practice only, and I think this unit is much easier. I found this unit much easier, just you have to be careful with that table, this fourth number table. Okay, once you form that right table, then you can easily solve the numerical. Okay, thank you. If you have any doubts, then you can directly contact me. Thank you.